All right. Hi, everybody, and welcome to this special session of the Spectral Geometry in the Cloud seminar. So today is one of our young researchers session, which means that instead of having the 1 hour long talk, we'll have 5 PhD students in spectral geometry who will give lightning talks, so 10 minutes each. And as such, I'll ask that this time to keep your questions at the end of the talks rather than during the talks, since they will be more time constrained than usual. For the first of those talks, we will have Tirumala Chakradhar from the University of Bristol who will tell us about Steklov eigenvalues, Steklov eigenvalue bounds for differential forms. Chakradhar, the floor is yours.
Thank you. Thanks to the organizers for this special session. So I'll talk about Steklov eigenvalue bounds for differential forms. Let me begin with the usual Steklov problem, which we know for functions, a quite popular one at this seminar. So we are looking at harmonic functions on smooth Riemannian manifolds with certain boundary condition involving this normal derivative of the function. And here sigma is the spectral parameter. We know that for compact manifolds, it has a discrete non-negative spectrum with finite multiplicities, and we also have this variational characterization from the standard spectral theory, which comes quite handy. So we could think of functions as zero forms, zero-degree differential forms. So in that sense, you could have generalizations of this problem to the setting of differential forms. There are various ones known, but the version that we talk in this talk is by Karpukhin from 2019. So these eigenvalue problems on differential forms are especially interesting from a topological perspective, in addition to the geometric structure, because of the connection between differential forms and the cohomology from the Hart's theory. So we have a smooth orientable compact Riemannian manifold with boundary. N is the dimension of the manifold, and we have P in the range of 0 to n minus 1. So P0 corresponds to the case of functions. So we look at harmonic forms, which are co-closed in the interior of the manifold. And on the boundary, we have this condition that the interior product with the outer normal of d omega is equals sigma times the pullback of the form to the boundary. Sigma is this spectral parameter. So like in the case of functions, we could associate with it a Dirichlet-to-Neumann operator, which is a bit technical to define here. And restricted to the space of co-closed forms, for P in the range 0 to n minus 2, we again have a discrete non-negative spectrum with finite multiplicities, which go to infinity. We also have an analogous variational characterization, which we'll use later. A quick notation. So in principle, you could have 0 as an eigenvalue for these, but we use these bold sigma letters to denote the non-zero eigenvalues, just for technical convenience. So now let me speak about the hypersurfaces of revolution, which are the main geometric objects of study for this talk. So here is a formal definition, but you could just look at these pictures. So on the left, you have, so basically have submanifolds of the Euclidean space. And the boundary could be, so it could be connected boundary like on the left, where you have a unit sphere in the Euclidean space, or you could have two boundary components like on the right. And this L shown in this figure, we call it as meridian length. And it so happens that if you look at the natural metric on this, the one induced from the ambient Euclidean space, that gives rise to a Bott product structure on these manifolds, which is of this form, dr2 h squared. This g Sn minus 1 here denotes the usual round metric on this unit sphere. We refer to this h as the warping function associated with this particular hypersurface of revolution. So we come to the eigenvalue bounds, the main topic of this talk. So let's begin with the case where you have a connected boundary, which is the unit sphere. So certain results were known by work of Coulbois, Girard, and Gittins from 2019 for the case of functions. We generalized these lower bounds to the framework of the Steklov problem on differential forms. So if you have dimension at least 3 and p up to n minus 3 halves, I'll come to this requirement later. So you have this sharp inequality. So you have a lower bound for the Steklov spectrum of M in terms of the Steklov spectrum of the Euclidean unit ball. And you have that the equality holds if and only if M is the Euclidean ball among this class of hypersurface of evolution. Another interesting feature is, so for functions, we have that in 2 dimensions. If we have 2-dimensional surface in satisfying the hypothesis which we had about the hypersurface of evolution, then you had that M was isospectral to that of the Euclidean unit ball. Here you have a little more flexibility. You could take any even dimensional manifold. And if you have P equals n minus 2 halves, then no matter which M you take, you have that the spectrum, the Steklov spectrum is exactly the same as that of the Euclidean unit ball. So the proof proceeds as follows. So for word product metrics, you have this special separation of variables, which helps in giving a nice expression for the Rayleigh quotients. And for the Rayleigh quotients, you'll have the warping function which I mentioned, and that comes with certain exponents such as n minus 2, p minus 3, etc. And it is from there you get this condition on p. You want the exponent to be positive or negative, depending on whether you want upper bounds or lower bounds, etc. So moving on to the case of 2 boundary components, we have similar bounds. The first one is a generalization of the lower bound from the earlier paper that so when you have the meridian length at least 2 and for p small enough, in particular up to half of n minus 3, you have the sharp inequality in terms of sharp inequality for the Steklov spectrum of M in terms of the spectrum for disjoint union of 2 Euclidean balls. So this is a generalization of this. And for small lengths, you have, for small p, you have a generalized lower bound in terms of the Steklov spectrum for the standard cylinder with a factor of 1 minus L over 2 raised to n minus 2p minus 1. And interestingly, for differential forms, you have a new type of upper bound, which is not done for functions. In fact, it's not relevant. Because like I said, the warping function h comes with a exponent of n minus 2p minus 1 and n minus 2p minus 3 there. And p is big enough, you somehow will be able to obtain this kind of new lower bound, new upper bounds, in addition to the existing lower bound. You also have another kind of, so now this result is for any L, could be small or large than 2. Again, so all these results which I'm, so this one, the generalizations which I'm mentioning, they are known for the case of functions from the paper of Coulbois, Girard, and Gittins. So these ones are the new ones. So for typically for low P, you're able to generalize these results. So likewise, we also have a generalization of an upper bound for the Steklov spectrum, again for small p, p up to half of n minus 3. With this factor of 1 plus L over 2 raised to n minus 2p minus 1, you have this comparison in terms of the Steklov spectrum of the standard cylinder. And again, you have a new type of low bounds for p bigger than half of n minus 1 with a similar expression in terms of the Steklov spectrum of the standard cylinder. And as a corollary, you note that of this theorem and the previous one, you have this corollary that for L less than 2, for P equals exactly half of n minus 1, you again have this isospectrality. Recall that earlier you have for one boundary component, this special feature of isospectrality happens for half of n minus 2. And for 2 boundary components, it's not even relevant for the functions. We don't have such a result about the isospectrality. But this case of differential forms, in this gives this interesting feature that P equals half of n minus 1. You have that the Steklov spectrum is exactly the same as that of a standard cylinder, no matter which n you choose. Okay, so with that, I conclude my talk. And so this is the archive ID for the paper. It has more such interesting results. So you have Escobar type lower bounds, and you also consider word product manifolds in general, rather than just hypersurface of level.
Thanks a lot for the talk. We have time maybe for one question. I actually had in your upper bounds that you obtained on the previous. So I mean, and these lower bounds and upper bounds when L is smaller than 2, they seem to degenerate at L equals 2. Is there some sort of better bounds that you can get combining both methods between 2 and 2 minus epsilon, or is that sharp?
These are not sharp.
Mm-hmm.
There was some attempts for functions about the sharp bounds by Leonard, but I worked on it, but there was some technical obstruction. I had to deal with some mixed boundary problems, which were to formulate where there was some obstruction in, I mean, you have to deal with the right kind of Hodge decomposition, etc. I don't know if that's what you asked, but anyway.
Yeah, oh, yeah. Thank you for this talk. It was a very nice talk, and I think we can get ready for the second talk of the day. For the second talk of today, we will hear from Maria Esteban from the University of Oxford, who will talk to us about the reverse isoperimetric properties of thick lambda sausages in the hyperbolic plane. So Maria, the floor is yours.
Yeah, okay, thank you so much for the invitation. So yeah, my name is Maria Esteban, and I'm currently a mathematics master's student at the University of Oxford. And now I will present a project on reverse isoperimetric inequalities in the hyperbolic plane. So this project was conducted with Professor Konstantin Drac as part of the Barcelona Introduction to Mathematical Research, which is a summer program that every year the Central Recerca Mathematica organizes. So I'm sure that some of you will already be familiar with the classical isoperimetric problem. So this problem is concerned on finding the volume with the largest volume, the body with the largest volume for a given surface area. So in the Euclidean space, the solution of this problem is, of course, an n-dimensional ball. So this problem has been thoroughly studied and generalized in different settings. So for instance, people have also tried to look at the opposite problem. So this is called the reverse isoperimetric problem. And now we're looking to find the body with the smallest volume given a fixed surface area. So this problem has kind of a trivial solution because we could just think of a body that is very thin and long, and what we call the flat pancake, as you can see in this diagram here. So yeah, this solution is obviously like not very interesting. So to avoid this degeneration of this body into this just long and thin body, what people do is to try to put some curvature constraints on the boundary of the body so that it's not too flat or too curved. So yeah, we'll formalize this in a second, but yeah, from now onwards, we'll be working with convex bodies, which are closed sets with a non-empty interior. So yeah, to solve this reverse isoperimetric problem, we will be putting some uniform curvature constraints on the boundary. So this can be formalized in terms of lambda convex and lambda concave bodies. So we say that a body is lambda concave, like a body in the Euclidean space, is lambda convex if for all the points on the boundary there exists an open neighborhood such that the intersection with the open neighborhood and the boundary of the body lies inside an n-dimensional sphere of curvature 1 over lambda. And then we say that the body is lambda concave if for all the points in the boundary there exists an open neighborhood such that the intersection between this open neighborhood and the boundary of an n-dimensional sphere of curvature 1 over lambda lies inside the body. So if the boundary of the body is C2 smooth, we can express these definitions in a more simple way. So then we can say that the body is lambda convex if for every point on the principal curvature of every point in the boundary is larger than equal to lambda. And we say that is lambda concave if the principal curvature of every point in the boundary is smaller or equal than lambda. So this definition of like lambda convex and lambda concave bodies has been generalized to the Riemannian setting as well. So in my project, we were working in the hyperbolic plane. So this definition will be exactly the same. And apart from we can look at, so apart from spheres, you can look at any other hypersurface of constant curvature. So for example, in the hyperbolic plane, we'll have 4 curves of constant curvature. We can either have circles and geodesics, and hypercycles, which are curves that are equidistant to a geodesic, or horocycle, which are curves whose perpendicular geodesics converge asymptotically. So yeah, we can have either of those 4 curves, but the idea behind the definition will be the same. So in Euclidean space, this reverse isoperimetric problem under uniform curvature constraints has already been solved. So for the lambda convex case, it was found that what the authors called a lambda lens was the solution to this problem, which is just the intersection of 2 spheres of curvature 1 over lambda. And for the lambda concave case, the solution is the convex hull of 2 balls that the authors called a lambda sausage. So in our project, we were trying to solve this reverse isoperimetric inequality in a hyperbolic plane. But in a hyperbolic plane, things become a bit more complicated. And the main difficulty when solving this problem is that the inner parallel bodies of convex bodies in a hyperbolic plane are not necessarily convex. So for example, if we look at this body K that I have here, so K is just the convex hull of 2 balls. So now if we take the inner parallel body, so we go like a row distance inside, the inner parallel body will be the concatenation of 2 disks with a hypercycle, where the hypercycle is the curve equidistant equidistant to the geodesics with a distant row. So this inner parallel body is not convex because it is well known that the region bounded by a hypercycle is convex in itself. So then we can find 2 bodies in the inner parallel body such that it's geodesic and doesn't belong to the body, as you can see here with these orange lines. So hence, in this example, yeah, the inner parallel bodies of this convex body is not convex, and this makes the analysis of this problem significantly harder. So what we did is to add a thickness condition. So we will only be considering what we call thick lambda concave bodies, which is bodies that are both 1 over lambda convex and lambda concave, which basically means that the curvature of the boundary of the body would range from 1 over lambda to lambda. So our main object of study was what we call a thick lambda sausage, and it's the convex domain bounded by 2 equal arcs of curvature lambda and 2 equal arcs of hypercycle of curvature 1 over lambda, as you can see in this diagram here. So in this paper, we're able to prove 2 theorems regarding the isoperimetric inequalities in the hyperbolic plane. So in the first one, we proved that given a thick lambda concave body K and a thick lambda sausage S, such that they have the same length, the area of K is larger than, it's always larger than the area of S, and equality only holds if and only if K is the thick lambda sausage. And related to this theorem, we also found an explicit lower bound for the area of a thick lambda concave body in the hyperbolic plane, as you can see with this expression here. And this, yeah, like the equality only holds if and only if K is the thick lambda sausage. So in this case, C is the curvature of the hyperbolic plane. So we also observe that as C goes to 0, this inequality that we obtain approaches the classical Euclidean result that was already proved in 2019. And also, if we set C equals to 1, our result is also analogous to the result that was obtained in S2. So this was just a sanity check of our theorems. And yeah, due to the time constraints, I will not provide the details of the proof, but the main idea was to construct a body that we call the thick convex hull, that we constructed using the cat locus. So the idea was that this body is contained in the body K, but by construction, the inner parallel bodies of this convex hull were convex. So then we used the classical like Steiner formulas that relates the area of the inner parallel bodies with the area of the outer parallel bodies to obtain these inequalities. We also obtained some results on the Blaschke's Hyperbolic theorem. So this is a classical theorem that says that if we have two closed, smooth, and strictly convex curves, such that the curvature of one curve in the points where the uninormals coincide is always larger than the curvature of the other curve in those points, then we can say that one curve rolls inside the other. And as you can see in this diagram here, maybe it's more clearly exemplified. So if one curve is a circle, then we can call this theorem the Blaschke and Rowling-Ball theorem. So this theorem has been also generalized into the Riemannian setting, but it doesn't hold true for lambda concave bodies in the hyperbolic plane, and hence it was never like addressed before. But in this paper, we proved that for thick lambda concave bodies, so for lambda concave bodies with this additional thickness condition, and then we have that a ball of curvature lambda indeed can roll inside K. And moreover, for every lambda prime that is strictly larger than lambda, we can construct a body such that a ball of curvature lambda cannot roll inside K. So for this, you can just think of the body that is the concatenation of two circles with two hypercycles of curvature 1 over lambda minus a small epsilon. Then the ball of curvature lambda will not be able to roll freely. But these were the main results of my projects. And if you have any questions, I'm happy to answer.
Thank you very much, Maria, for this very nice talk. We have time maybe for one question.
Would there be, so you put the curvature constraints, would there be any other kind of constraint that you could think of or that have been studied?
I think curvature constraints is usually what has been studied because it makes like the problem like flexible now that it's still like quite interesting to solve, but yeah, probably one can define more strict constraints.
Thank you for the question, and thank you, Maria, for this talk. I encourage anyone who wants to know more to write to Maria after this. And for the third talk today, we will hear Samuel Audet-Beaumont from Université Laval will tell us about constructing surfaces with first Steklov eigenvalue of arbitrarily large multiplicity. Samuel, the floor is yours.
Thank you. Okay, so I just want to start by thanking the organizers for inviting us. That's really a great opportunity. I also want maybe to present myself real quick. So my name is Samuel Audet-Beaumont. I'm a PhD student at Université Laval under Alexandre Giroir. And today I will talk about constructing surfaces with first Steklov eigenvalue of arbitrarily large multiplicities. So let's get into it. We don't have that much time. So there's the Steklov problem. That's the classic Steklov problem slide. Since we've already had a talk today about the Steklov problem, I will go very fast over this one. The idea here is mainly to take in the notation. So for us today, MG will be a connected smooth compact Riemannian manifold with boundary. And we will start the numbering of eigenvalues at 0. So what we're going to talk today more specifically is the multiplicity. So what is multiplicity? It's simply the number of times an eigenvalue is repeated in the spectrum. Another way to define it is simply by taking the dimension of the associated eigenspace. So for maybe a trivial example, we can talk about the eigenvalue 0, which corresponds to sigma 0. It is associated to constant functions, just like in the Neumann problem. And we get that the multiplicity of this eigenvalue is always equal to the number of connected components of M. Here, in our case, since we always have connected manifolds, it's always going to be 1. Now, for the next eigenvalues, things are not that simple. Today, we will focus on the first non-zero eigenvalue. So for the first non-zero eigenvalue in dimension 2, we have upper bounds. So here we have the upper bound by Karpukhin, Kokarev, Polterovich, which bounds the multiplicity of the first non-zero eigenvalue in terms of the genus. There are a lot of such bounds. Also, this bound was also proven by Fraser-Schoen and Jam independently, so you can go see these papers as well. And there are other bounds, but they all feature the same things, like the genus, sometimes also the genus and the number of boundary components. Now, why focus in dimension 2? Well, it's simply because in dimension 3, no such bounds can exist. We have a prescription result by Jam, which implies that we can prescribe a finite number of eigenvalues at the beginning of the spectrum on a given manifold. So in particular, you can prescribe as much multiplicity as you want, no matter the topology. So it might be interesting to see what can be done if we add additional constraints, but it's not the goal of the talk today. So we will stick to dimension 2. Now, if we get back to our famous bounds, multiple questions can be asked in this context. One of them being, is there a universal bound? What I mean by a universal bound is is there a maximal multiplicity such that no matter the genus, no matter the number of boundary components, one cannot exceed in dimension 2? And this is the answer that, this is the question that we will answer today with my main result. So my main result is a construction result. For each prime P, there exists a compact orientable Riemannian surface SPGP of genus such and such that we have multiplicity greater than P minus 1. So essentially, we can construct surfaces with as much multiplicity as we want. So there can be no universal bound. Of course, since the multiplicity goes to infinity, the genus must go to infinity as well, so as to not contradict the previously stated bounds. Also, I want to note the growth of the multiplicity here in terms of genus is of square root of g. This will play a role later on, but for now, I'm just going to leave it at that. So how do we prove such a result? Well, I'm just going to do a very fast overview of the proof. So the proof is based on a technique by Marc Berger and Bruno Colbois. It was originally used to prove a similar result for the Laplacian spectrum. So the way we do so is we take a group, a specific group with nice properties, and we build a surface around this group so that the isometry group of the surface contains this specific group. Now we have an action of the group on the surface, so it induces an action of the group on each eigenspace just by precomposing eigenfunctions with the action of the group. And this action is also linear, so we get a representation. And thus, we can use the tools of representation theory. So by the tools of representation theory, we can now decompose this representation in irreducible representations. And then we take the group G to have an irreducible representation of I degree, and we want to show that it acts on E1. The way we do so is simply by using some properties of the groups and some properties of the Steklov problem. I won't go into much details into that. If you have questions, don't hesitate. But the main idea is here. So now, if we continue, there are some other questions that we can ask about these bounds. For example, we know that none of the bounds that we know right now, none of the general bounds, are sharp for all genus. In low genus, there are some examples where we can find what is the exact optimal multiplicity that can be achieved. And there's a gap, there's always a gap between the general bounds that we have and these explicit calculations. So the question to ask is, what is the optimal bound? And there is a conjectured optimal bound. And that's why I'm talking about that today. It's simply to compare this optimal bound, this conjectured optimal bound, with the construction that I've made. So the only problem is that the conjectured bound is not exactly in the same setup. So I will take a little bit of time just to talk about the inhomogeneous Steklov problem. So the inhomogeneous Steklov problem is very similar to the Steklov problem, except we add densities gamma here and rho here. Of course, if those densities are equal to 1 everywhere, we get back the classical Steklov problem. Now, we also have all the nice properties that we know and love about these problems. So it's a discrete, non-decreasing spectrum with no accumulation points, starting at 0, etc. Now, what is the conjecture in this specific case? Well, it's a conjecture by Jam in 2016. So maybe two things about this conjecture. So if we start on the left-hand side, we can see that the supremum here is not taken only on all metrics G on M, but also on all densities. So we have more degrees of freedom here. So this optimal bound might be bigger than the sup previously stated. Also, if we look at the right-hand side, here we have CHR0 of M, which is a topological invariant. It's called the relative chromatic number. And it corresponds to the degree of the highest degree complete graph that can be embedded in M, such that the vertices are mapped to the boundary of the surface. So it's quite abstract, but Jam also provides some estimates about this quantity. His estimates are way more precise than these ones. I just wanted to show that this invariant grows like square root of g, which is exactly the same growth as the constructions that I've provided. The constructions, however, my constructions, however, are not sharp in terms of the conjectured bound, but they are sharp in terms of the growth of the conjectured bound. Also, JAM provides this lower bound here, and this lower bound is given also by some kind of constructions, but these constructions are using what we call transversality arguments. And in order to use transversality arguments, you need some degrees of freedom. So it absolutely needs the degrees of freedom afforded by the density functions here. So without these density functions, it's not clear a priori that we can have such constructions for the usual Steklov problem if you fix these density exactly to 1. So that's pretty much all I wanted to say for my talk today. I don't want to go into too much technical details, so I will leave you with this slide, and if you have questions, don't hesitate.
Thank you very much, Samuel, for the talk. We have time maybe for one question now.
Can I ask if the technique for finding the representation, so I guess it's the last point in the previous slide, are you using anything beyond the coordinate domain theorem?
Anything beyond what, sorry?
Nodal domains, the nodal picture, the fact that first eigenfunctions have no more than 2 nodal domains.
You mean in the construction, if I use something beyond nodal domains?
In proving that you have a high degree representation in E1.
What I use, I don't use nodal domains. You quotient by a subgroup, and then you get a different surface, and then all representations of low degree go to this surface except for the one of high degree, and then you show that the eigenvalues do not correspond. So you do so by pinching geodesics mostly.
Misha, for the question, and thank you, Samuel, for this nice talk on the multiplicity. Again, I encourage anyone that has further questions to contact Samuel after this the seminar today. All right, and so for the fourth talk of the day, we will have Lo from King's College London, who will tell us about homogenization for the Robin eigenvalue problem on manifolds and flexibility of optimal Schrödinger potentials. Lo, the floor is yours.
Thank you for the invitation and for the introduction. Sorry about the cold. Well, it's a short talk, so I think I'll get right into this. So the kind of problem I'm interested in is something like this. The prototypical example is I take a domain, I poke a bunch of holes in it, and then I look at the some sort of PDE on it. And as these holes become smaller and more numerous, the kind of question we ask is, well, what happens to this series of solutions in the limit? So for this particular example, it's known that if the holes are proportionally large, then these solutions collapse to 0. If the holes shrink very quickly compared to the distance between them, then they somehow become invisible in the limit, and we get the solution of the equation we started with on the entire domain. But it turns out that there is a way to design these sequence of perforated domains so that a secret third thing happens, which is we converge to the solution of an equation, not the one we started with, but this what we call the homogenized equation on screen with this extra term in it. So you might be able to imagine why this would be interesting to, for example, someone who's interested in the physics of porous materials. But this is a spectral geometry seminar. So what I'd like to do today is to share a few examples of how this idea of homogenization has been a useful tool in investigating spectral problems in a couple of short examples, the third and last one of which will involve some work done as part of my PhD at King's College. So I'm fortunate that two of my previous speakers have already introduced the Steklov eigenvalue problem, though with, I'd have to say, with a different convention on the labeling of eigenvalues. And a natural question to ask in this case is, well, how big can you make the first non-trivial one, which for me is lambda 2? When this question is posed on planar domains, we have the classic Weierstrass inequality, which says how to maximize as a disk. This question posed on orientable surfaces, we have a handful of inequalities. For example, this one from Kokarev. So what can homogenization do for us in this case? So on screen is a recent result from two authors who I think are both in the audience today. So what was shown is that in a similar way, you can design a family of perforated domains. In this case, so that the Steklov spectrum on this series of domains converge in the limit to that of the Laplace problem on the manifold without perforations. Now we can compute the Laplace spectrum for example, a sphere, and what this gives us is an example that shows us that this inequality on the previous slide is in fact saturated. You can get Steklov eigenvalues as close to 8 pi as you want. Now, of course, I'm glossing over a lot of details here. Perhaps the most important of which is that we've started doing this homogenization business on surfaces and manifolds. And so an important part of the work is to be able to find a substitution for this concept of evenly distributed holes that was avoided to us in the Euclidean case by means of a periodic structure, which we don't have in general. Now, we know that the disk gives us the biggest first non-trivial Steklov eigenvalue. In the other direction, we could perhaps ask, if we know that our domain has an eigenvalue close to the maximal, do we also know that this domain is going to be close in some sense to the disk? This is a problem that makes sense to be asked of many optimization problems in general. And when the answer is affirmative, sometimes we say that the problem exhibits stability, and we say that it is flexible otherwise. And of course, all of these notions depend on this notion of proximity that we decide to consider between pairs of candidates to our problem. So for example, the Weierstrass inequality again is flexible with respect to the Hausdorff distance. This can be proven by a method that also uses idea from homogenization. Instead of poking little holes in the interior, what is done in this case is taking any two domains, if we can introduce little oscillations on the boundary, and in this way we can make we can modify the Steklov spectrum of one domain such that it becomes arbitrarily close to that of another, and in particular this gives us flexibility. But also part of this proof involves the idea of identifying a conformal domain with a corresponding measure defined on the boundary of the disk. And in fact, we find that if we consider a suitable Sobolev norm between on the space of measures on the boundary of the disk, then we instead recover stability for the Weierstrass inequality in this case. So for the last example, let's switch to the Schrödinger problem on the manifold. So the main result in this case is that for sufficiently regular potentials, it is possible to design once again a series of perforated manifolds such that the Hopon spectrum on these family of manifolds converge to that of the Schrödinger spectrum on the right-hand side. And an application this gives us is by means of thinking in a weak sense that the Hopon eigenvalue problem is really a Schrödinger problem with the potential concentrated on the boundary. We have some examples of flexibility of Schrödinger potentials. So in the remaining time, I won't try to give the proof, but I hope I'll be able to impart some kind of idea of why we expect this kind of result to be true. So the thing we do is we take the weak formulation of both of these problems, we kind of squint at them a little bit, and see that the discrepancy is exactly these terms highlighted in red. And the idea that guides this construction is that we choose these, we design these perforated domains so that the quantities in red on top in the limit converge to those on the bottom. So what we do in practice is, as in the example we have seen, we split this domain into many small Voronoi cells. On each cell, we poke a hole in it, and we gather the potential, a Schrödinger potential on that cell and concentrate it onto the boundary of that hole. In the way I've just described it, this concentrating procedure decides how large the boundary parameter should be. But we find that we could also do the opposite, which is to fix the boundary parameter to begin with. And now this procedure decides how large the hole should be. So all in all, we end up with something that sort of looks like this, where we get bigger holes where, for example, the potential is larger. And so this is how we get Hoban to Schrödinger. And how does this in turn gives us flexibility to Schrödinger? Well, this is let me quickly explain this last bit on this final slide, which is that once we've shown this homogenization that takes us from the bottom picture to the one on the left, we realize that we can fill the holes back in and then smooth out the concentrated potential by a little bit without changing the spectrum too much. And so this gives us, in fact, a family of smooth potentials that we see on the right-hand side here that we can show are, in fact, separated in some Sobolev dual norm from the potential we started with. If I have a few more seconds, I'd like to finally quickly point out that these statements have been written this way so that they fit on the screen. We can, in fact, do a little better. We can do manifold with boundary. We can do slightly worse regularity. We can change sign on the potential. And finally, similarly, down below, these restrictions on the dimension, we can also do this in dimension 2, but we have to be a little careful about the some function space embeddings. And that's my talk for today. Thank you for your attention.
Thank you very much, Lo, for the talk today. We have time again for maybe a question. Do you think we could use this to somehow find optimal behavior for the Schrödinger problem in different contexts, maybe not just optimization for positive potential, but given that you can work with negative potential as well? Or do you think there's more to investigate about the Schrödinger problem using using these tools, say, past just optimization for positive potential?
Yeah, maybe like sorry. One obstacle I can see to this is somehow a lot of these results I'm drawing from to prove this flexibility result in the end. They're really stated for the case of potentials that do not change sign, and so I can see the possibility of such a thing being done, but yeah, it's probably difficult. Sorry, this is a bit of a nothing answer, but
no, I mean that's all right. Well, thanks again, Lo, for this talk, and
thank you.
Once again, further questions can be left for after the talks for today. So I think we are now getting for the last talk of the day. We'll have Loïs Delande from the Institut de Mathématiques de Bordeaux, who will tell us about a sharp spectral gap for degenerated Witten Laplacian. Loïs, the floor is yours.
Thank you. So first, I want to thank the organizers for the invitation. And so, yeah, so this is the subject of my talk, degenerate Witten Laplacian. So let's start first with Witten Laplacian. Since we are in a geometry seminar, I'll start with the geometric origin of this Laplacian. So taking a compact manifold or RD and a smooth potential, you can construct the Witten Laplacian just as the standard Hodge Laplacian acting on p-forms, but you deform the exterior derivative by a function exponential minus v over h. You twist the derivative, and then you get the Witten Laplacian. Here I work in a semi-classical framework, so I have the semi-classical parameter h. And so this is the general setting. In my talk, I will just be in the case where x is Rd and p equals 0. So I'm interested in the Laplacian acting on functions, not all p forms. And it has a more usual definition, which is minus h2 Laplacian plus a potential, a semi-classical potential. So it is a Schrödinger operator, and it can also be recovered from the generator of an overdamped Langevin process, which justifies a bit more the study of its of the bottom of its spectrum. So that's what I'm interested in here. But what are the things that exists? So yeah, I should say that from the definition of this Laplacian, you can all see that it's self-adjoint, or at least it admits self-adjoint extensions. It also is non-negative, and if I'm on Rd, I need a confining assumption to have the essential spectrum far from 0. Well, that's one reason to have this confining assumption. And if the potential is a Morse potential, so with non-degeneration, I have a finite number of minima that I will denote in this whole talk n naught, and I will also denote u naught, the set of minimas of V. Then you have a rough localization of the small spectrum of the operator, and you have a more precise estimate that was obtained 20 years ago. So basically, what does this theorem say? It says that the eigenvalues smaller than h are exactly described. So first you have as many eigenvalues as you have minima, and you can very well describe how they look like. So you have prefactor h exponential minus 2 s of m over h, and some rest. So this is done in a Morse setting. What we can ask is, what if V is not Morse? So there has been some work in recent times. So you can do similar results for Morse bot functions. So with manifold as minima or critical points. You can also do things in the probability side, so what I call transition time estimates. And in a very general setting, you can have Arrhenius law. So Arrhenius law describes the S in the exponential. And so what is my setting is I consider potentials that satisfies what I call a degenerate Morse lemma. So what you see here, the equation is just like the result in the Morse lemma if the nu in blue are equal to 2. Here I assume, it's not a result, I assume that my potential satisfies such an equation with some nu's that can be greater than 2. And under this assumption, I can have a rough estimate, a rough description of the eigenvalues. So on So for small eigenvalues, what I mean small is smaller than h to some power. Here it's 2 minus 2 over the maximum of the news. I have the same result as before. So I have n0 eigenvalues counted with multiplicities. I recall n0 is the number of minima of my potential. And they are exponentially small. For now, I don't describe exactly how exponentially small, but I will come to that. And I have a spectral gap. Let us notice that if my potential is Morse, the nu in blue is equal to 2, and so I recover the bound in h to the power 1, so it is sharp in that sense. So then I want to deepen the results and to have a precise description of the lambdas. And what I want to do is to use a WKB method to have a sharp description of the eigenvalues. And these constructions are made around a saddle point. And so I rely on some work done before to have a very sharp estimates in the Morse setting, and I want to adapt them in the non-Morse setting. So that's where the form of the cutoffs before the exponential minus v over h comes from. And all this leads to two equations, or I should say a system of equations. The first equation, which is highly nonlinear, we call it the aconal equation. And then I have a series of equations that we call transport equations. Usually the transport equations are really easy, not really, but usually easy to solve as long as the transport operator is invertible on good spaces. And the aconal equations is often seen as an eigenvalue problem, where here the lambda, the nabla L naught squared is seen as an eigenvalue. But here I cannot really do that. The general method is to look for the stable manifold theorem in the WKB method. Then you say that this manifold is Lagrangian and it projects nicely on X space, and in some way there, then you obtain your function L naught that solves the aconal equation. Here we cannot do that. There may be some stable manifold theorem. If I have such manifold, it should be Lagrangian, and if it is, it may automatically projects nicely on the X space, but I have hints that it should not always work. So I will present them just after. And then for the transport equations, in fact, the transport operator is not invertible on the good space in general cases. So I have to restrict my study to more precise potential that I call admissible potentials. And for such potentials, I have the following result. Well, I have the complete Ehring-Kramers law, so I have the same as before, except that my h befriend the exponential has some power. In the Morse case, this power is always 1, but here it is not. And I'd say that what is an admissible potential, where I described here some kind of admissible potential, not all I could find, but some. And we can see it is rather easy to construct non-admissible potentials. I put here one. So minus x to the 4 plus y to the 4 plus z to the 8. It's a bit simple, but it doesn't work in my constructions. And yeah. Time is up, so I will not develop in what I could do next, but yeah, thank you for your attention.
Thank you very much, Loïs, for this talk. Do we have questions. Now maybe time for one again.
So for your example of a potential that's not admissible just before, is it just that it doesn't satisfy the admissible hypothesis, or does it really not work in the proof?
In fact, I need it does not satisfy the admissible condition, and in the construction, in the WKB constructions, I cannot do much with this potential, and I cannot hope to have the eigenvalue, the sharp description of the eigenvalue. Yeah, I just cannot. So it's a bit strange. In fact, what I obtain is here in the result, the power beta in front of h may become 0. So I don't have information, or worse, it may become negative. So this just completely destroy my estimates.
Okay, thank you.
Thank you very much, Laura, for the question, and thank you, Loïs, for the talk. So I think that today we've seen 5 times that the future is probably quite bright in spectral geometry. I think that we're looking forward to the next session of this young researchers in spectral geometry that will hold in the next semester. Until then, I think we can thank again our 5 speakers for the day. And we will reconvene next week with a talk by Charles Bordenave, who will tell us about random perturbations of Toeplitz matrices. So thanks, everybody, and have a great week.
Thank you to all the speakers. That was really great.